C has the advantage of a high-level language in its logic flow control and the way it can be used to organize your code, and it also has the advantage of assembly language in the way it can manipulate bits. This lesson is about floating point bits and how you can get to them. There is some variation in the exact format of the bits in a floating point number. Most common is IEEE 754, and most modern floating point formats are very similar to it. This is the layout of a 32-bit floating point number. One bit is used for the sign bit. Positive and negative floating point numbers are the same. This bit set to 1 indicates that the number is negative, and 0 specifies that it's positive. The 8-bit exponent is in what is known as the excess bias format. It's 8 bits long, so it can represent 256 values. Its nominal value is 127, which is the normal exponent value for a number 1 or 2, but the variation of the exponent can be positive or negative to represent the decimal point being moved to the left or the right. Actually, it's not a decimal point because this is a base 2 number, so it's actually a binary point. The 23 bits of the fraction represent the digits of the number itself. The fraction is normalized. That means it has been shifted over so it has no leading zeros. Any leading zero values are represented by adjusting the count of the exponent value. Actually, it has been shifted 1 bit further than that. The first bit is always 1, so there is no need to save a place for it. With the fraction portion being 23 bits in length and the leading bit being implied, it looks like you have 24 bits of accuracy, and in a way that's true. But by the time you perform some math, the accuracy drops. Approximations build up fast. It's that creeping approximation that gives you problems if you try to use floating point numbers for monetary calculations. There is no unsigned float. This comes from the fact that the complexity of representing floating point numbers is large enough. Adding an unsigned float would only add 1 bit to the precision of the exponent, and it would double the complexity of floating point operations. Some values are special. Other than regular normalized and unnormalized values, 3 have been defined. If all the bits are set to 0, it is actually 1 times 2 to the minus 127th power. That's a very small number, but it's not 0. So for convenience, the fraction and exponent being 0 is special. It's defined as 0 for floating point operations. By the way, there is both a positive and negative 0. Another special definition is infinity. You can have both positive and negative infinity. Infinity results from dividing by 0. One special case is called NaN, not a number. This comes from performing an operation that isn't defined, like dividing 0 by 0. You can look inside the floating point values on your system. All you need do is declare a union with the floating point number you want to analyze with an array of unsigned 8-bit integers. You can assign a value to the floating point number and look at the bits in the integers. This program displays the value of the floating point numbers followed by the values of their bytes. What you get from this may not be what you expect to get. The problem comes from 2 places. First, the format of the floating point numbers in your C compiler may not be the same as those I've described here. Second, the Intel chips reverse bytes, so things don't show up in their real positions. To really dig into the internal formats on your computer, You will need to experiment by storing different values in the floating point variables of this program and see what happens.